Hi, today I'm going to explain about the properties of Z transform. There are 9 different types of properties such as linearity, time shifting, scaling in Z domain, time reversal, time expansion, convolution, differentiation in Z domain, initial value theorem, and final value theorem. So these are the 9 properties in Z transform. So first of all, let us go for the first property, that is called as linearity property. What is linearity? A system is said to be linear if it satisfies the principles of superposition. So in the last class, we have discussed about the properties of signals. The similar linearity is also been applied, but it is been applied in the Z transform. So why we are using the Z transform? Z transform is nothing but we are trying to see that the signals, the wider signals can be converged by using this Z transform. Whereas the signals in DTFT does not converge, but in Z transform it converges. So what are the properties that are used in Z transforms? And these are the 9 properties. The first of all is the linearity property. If you go for the linearity property, so I told you linearity is mainly based on superposition theorem. For an example, if you take two signals x1 of n and x2 of n, these two signals we wanted to convert to the Z transform. Now you can see this x1 of z is converted to the Z transform and we are going to get capital X. You see the difference between the input is been taken as small x1 and the output is been taken, which is there in the Z transform, is capital X1 of z with the ROC. You know what is an ROC? It is called as region of convergency. Region of convergency mainly depends upon the alpha value, that is nothing but your R1. The second signal is X2 of n, which is nothing but we are taking the Z transform as X2 of z with similarly with the region of convergency R2. Now these two signals we are going to add up. While we are adding, we are going to take the a1 into x1 of n plus a2 into x2 of n. a1 and a2, they are called as weighted factors. They are called as vector. And this input signal, we have to convert it into the Z transform. So when we convert, it is already represented that x1 of n is nothing but your x1 of z and x2 of n is represented as x2 of z. With your ROC, at least R1 should be intersect with the R2. So this is the statement of linearity. This is the statement of linearity. So we know that linearity is nothing but it is going to perform like superposition theorem. So what is the proof here? It is x of n is nothing but your input signal. This input signal is been converted into a Z transform. To convert it into the Z transform, we have to take x of z. X of z is nothing but this is the formula that is being used to represent the signal, that is summation n is equal to minus infinity to plus infinity x of n into z to the power of minus n. Now what is our x of n? X of n is nothing but your the input signal. This is your a1 into x1 of n plus a2 into x2 of n. This is our input signal. Now this input signal we are applying as a Z transform here. So using this formula, what is our x of n? X of n is nothing but this formula. That is x of n is been taken as a1 x1 of n plus a2 x2 of n into this signal is been multiplied with z to the power of minus n. So just we have substituted our input signal into this formula. Now you can simplify this. You have to bifurcate the signals. You can see that is we are simplifying it. We are separating the two input signals, that is n is equal to minus infinity to plus infinity a1 x1 of n into z to the power of minus n plus summation n is equal to minus infinity to plus infinity a to a into x2 of n. If you see this individual term is nothing but your x of z. Since suffix we have taken it as an x1, we represent this one as x1 of z, and a is nothing but your weighted factor. So this is a1 multiplied with x1 of z plus a2 x2 of z, and hence the linearity is been proved. So now let us go for the another property which is called as time shifting. We know that time can be shifted either positive or towards the negative, or incrementing or decrementing it. We can either increment or decrement. For an example, now we are taken here, if x of n, this is an input signal. You can see this is your input signal. Now you are applying your z transform. When I apply for the input signal, it is normal x of z with ROC as R. Now for the input signal, what I am doing here, it is now I am applying the time shifting, that is n is nothing but your sample value x of n minus n naught. This minus n naught is nothing but a time shifting value. This is nothing but z to the power of minus n naught. N naught is nothing but your time shifted value multiplied with your x of z with ROC is equal to R, except for the possible addition or deletion of the origin or infinity. This is the statement of the time shifting. Now let us prove this one. So we have taken we are taking the z transform, that is z of x of n is nothing but your x of z. We know this formula, that is nothing but summation n is equal to minus infinity to plus infinity x of n into z to the power of minus n. Now what is our x of n? X of n is nothing but x of n minus n naught, that we are applying here. X of n minus n naught multiplied with z to the power of minus n. So now we are just simplifying it. What we are doing it is the x of n minus n naught, we are taking it some variable. You can take as L or M or any variable you can apply it. So what we are just simplifying, x of n minus n naught, this term we are writing it as L, and this is been multiplied with z to the power of minus n. Minus n. What is minus n? You can see from here. What is n value here? How you are going to get your n value? N value is nothing but L plus n naught. So the same value we have been substituted here. So it is just a simplification. X of L, z to the power of minus L, z to the power of, and this is all the simplification value. You can just check it out. Z to the power of minus, you take it outside, and this is simplified, and this term is nothing but your x of z. So you can observe that z to the power of minus n into x of z, hence we have been proved. Now let us go for the next property, that is scaling in z domain. Scaling is nothing but a multiplication factor. And what is its statement here? It is, if x of n, as usual we are taken, if x of n, when you take a z transform, it is x of z with ROC is equal to R. So this is called as a scaling factor, complex number, alpha to the power of n into x of n. When I apply the z transform, you have to get x of z by alpha with ROC is equal to magnitude of alpha. The third property is scaling in z domain. So let us first define the statement that is nothing but if x of n is, when you apply the z transform, it is x of z with ROC is equal to R. So what is the input we are applying here? It is nothing but, it is scaling is nothing but, this is called as a scaling factor alpha to the power of n into x of n. When you apply the z transform, you have to get x of z by alpha with ROC is equal to R, and alpha is nothing but your magnitude value, where alpha is a complex number. So this is a statement. Let us prove that. As usual, we know that take the formula x of z is equal to x to the power of n into z to the power of n, and substitute your x of n. X of n, what is that? Alpha to the power of n into x of z, x of n into z to the power of minus n. So now you go for simplification. So just you are simplifying x of n into alpha to the power of minus n into alpha to the power of n. You simplify this, you are going to get x of alpha to the power of minus n into z. Then this is called x of z by alpha. Next, if you go for the fourth property, that is nothing but your time reversal property. Time reversal property is same, you take input as x of minus n, apply your z transform, your output will be x of 1 by z with ROC is equal to 1 by R, here it is. So as usual, you take the formula x of z is equal to summation n is equal to minus infinity to plus infinity x of n into z to the power of minus n. Apply your x of n is nothing but your x of minus n we have applied. Simplify, take this minus n as L value. So substitute it, simplify it, and you're going to get x of 1 divided by z. The next property is nothing but your time expansion property. If x of n, when you apply the z transform, you are going to get x of z with ROC is equal to R. Then what is the input now you're taking for time expansion is x of k. K is nothing but some value variable of n. When you apply for this z transform, you are going to get x of z to the power of k with ROC is equal to R to the power of 1 by k. So where x of k into n is equal to x of n by k if n is an integer multiple of k is equal to 0. Otherwise, if x of k as k minus 1 0 inserted between successive values of the original signal. What is this k value? K values, how many zeros you are inserting here, that all depends upon the variable what you are taking. That is, k minus 1 zeros are inserted between the successive values of the original signals. That is called as a time expansion. How many zeros you are going to be inserted here. So this is a proof here. Say same thing, you're going to substitute here. Take the formula x of z, uh, summation n is equal to minus infinity to plus infinity x of n into z to the power of minus n. When you substitute the value, you're going to see that that is the coefficient of the term z to the power of minus n equals 0 if n is not an integer multiple of k, and it is equal to x of n by k if an integer is a multiple of k. Thus the reverse transform is x of k into n. K is nothing but the number of zeros. K minus 1 is nothing but the number of zeros that you are inserted between a successive values of original signal. The next that is property is the convolution property. Convolution is nothing but multiplying the two signal. You're taking one signal x1 x of n, you're taking another signal x of, that is nothing but y of n. When you apply the z transform like this, here you can see x of n, this is called convolution into y of n. When you apply the z transform, you are going to get x of z into y of z. So as usual, apply the what is your input. Input is nothing but here x of n into y of n, and when you are applying for a convolution, this is a formula that is used for the convolution, that is x of n convoluted into y of n is nothing but x of k into y of n minus k. So you apply that input here, that is summation n is equal to minus infinity to plus infinity. So this is your x of k into y of k into z to the power of minus n. So now we are just simplifying, that is interchanging the order of summation, simplifying it. Put this value n minus k as some variable here. So substitute it, simplify it, and then you can write this x of k into z to the power of minus k, and this term is different. When you see the individual term, this term is called as, the first term is nothing but your x of z, and the second term is nothing but your y of z, and hence it is been proved. The seventh property is nothing but differentiation in z domain. You can also differentiate it. So you can take the input n into x of n is, when you apply the z domain here, you're going to get minus z d by dz into x of z. As usual, you can apply the proof here. What is the proof? Apply the formula here. X of z is equal to summation n is equal to minus infinity to plus infinity. Here, what is your x of n? X of n is nothing but n into x of n. And for this above equation, you can apply the differentiating on both the sides with z here. So you can differentiate d by dz of x of z is equal to summation. When you differentiate with respect to z value, it is z to the power of minus n minus 1. So this is a simplification factor. When you simplify it, you are going to get it as minus z d by dx into x of z, and hence it is being proved. Next, the property is initial value theorem here. This is a very important theorem, initial value theorem and final value theorem. So if x of n is equal to 0 for n is less than 0, then x of n is a casual value. Then you're taking this. So this is a formula. You apply the formula. Here x of n is, you go on substituting from 0 to infinity values here. So x of 0 plus x of 1 into z to the power of minus 1 and so on. And take the limits on both the sides here. So when you take the limit, your RHS will become your 0, and hence it is been proved. The last one is nothing but your final value theorem. The final value theorem is nothing but same formula you can apply here. Put x of n plus 1 is a final value. Simplify it. Take the limits on both the sides and simplify it, and hence your LHS is being proved on RHS. Thank you.